Welcome everyone. This is an overview of the course entitled Nonlinear and Adaptive Control. I'm going to start by giving an overview about the contents of this course. As we know, in control systems in general, we normally start by talking about the models, then analysis, and then we do control design. This course is actually no different from this sequence, so I'm going to start by talking about the nonlinear systems from the modeling point of view. So we'll see the mathematical form of the models that could represent nonlinear systems, and we specify the class of systems that we are going to deal with. In general, we are going to deal with systems represented in the state space formulation by a set of first order nonlinear dynamical equations. So we'll introduce some of the basic concepts related to that, because nonlinear systems, in order to have solutions for them, then the nonlinearity has to satisfy specific conditions. So we'll talk about that. We'll also talk about a very important phenomena in nonlinear system, and that's the phenomena of equilibrium points. In linear systems, usually we don't talk about equilibrium points, because if the system in the form x dot equals ax plus bu, if a is non-singular, and we talk about the equilibrium, we talk about actually in case of zero input, we talk about the origin, and that's it. However, in nonlinear systems, we will find out that we could have more than one equilibrium point. And again, as in a usual sequence in a control system, we start by talking about second order systems. The reason for that, of course, there are some physical systems that can be represented in the second order form. However, in addition to that, in nonlinear systems, we will be able to visualize the performance of the system using a space which consists of the two states. Suppose that they are x1 and x2. We call that the phase plane states, and we can draw the trajectories that represent the solution for second order systems. We will study both actually linear and nonlinear second order systems in the phase plane, and see how we can benefit from the analysis of linear systems in studying nonlinear systems. The next step is an analysis step, and this is of course the study of stability, which is very important in all dynamical systems as a property. However, in linear systems, we are used to talk about stability of systems, while here in nonlinear systems, we'll talk about stability of equilibrium points. We'll explain why the difference exists, and we'll show how to characterize the stability of an equilibrium point. We'll see that there are different classes of stability, like local stability, global stability, exponential stability, and so on. So we'll see that when we study the stability of equilibrium points. Now, once we finish this analysis, we'll move on to the design of controllers. And again, normally when we study controllers, we start by state feedback controllers. However, since we are talking about nonlinear systems, then there are special techniques that we could use in order to stabilize nonlinear systems. We'll see that. And of course, we know that models contain uncertainty, and the uncertainty could be classified either an uncertainty in the parameters, like we don't know a certain parameter value for sure, or in modeling, which means that for simplicity we try to use low order models to represent systems and base the design on that low order model, so we ignore some of the dynamics So in order to guarantee stability, there are two techniques. The first technique, we will do it in the nonlinear context. It's called the robust state feedback stabilization. Specifically, we will concentrate on the sliding mode control algorithm. We'll see how to develop that. However, we can also deal with uncertainties using adaptive control, which is a method that can be used to estimate the system parameters or the system model online, and consequently design the controller so that it can perform in a way that we specify. So we'll talk about model reference adaptive control. In that case, we would design the controller such that the output of the real system would follow the output of a certain ideal reference that we would like to have. So we'll see how to do that, and of course we have to guarantee stability, so we'll base our design on the analysis of nonlinear system as we have explained it before. And of course adaptive controllers are actually a class of nonlinear controllers. That's why it's included within this course. The model reference adaptive control is historically developed in continuous time, so we'll do that. But also there is a class of controllers which is called the self-tuning regulators, and this is developed historically again in discrete time. So in order to understand how to do parameter estimation in the discrete time, we'll do parameter estimation based basically on the least square algorithm, and see how we can use that to design what's called a self-tuning regulator. And of course there is an analogy between model reference adaptive control and self-tuning regulator, but as I said, historically they were developed separately. Another type of adaptive controllers would be the gain scheduling controllers, which is very common in flight control, where the operating point will depend on the speed and the altitude of the aircraft. So at each operating point we would use a different controller, so we switch between different controllers based on the flying conditions, and that's what's called gain scheduling, changing the controller based on the operating point of the given nonlinear system. So we'll talk about that, and finally we'll end up with talking about the adaptive observers. As we know that most of the time we cannot measure the states of the system, so we have to rely on the output. So we'll use the output, and depending on that we conclude the states of the system. So we'll give an idea about the adaptive observer at the end of this course. The main textbooks that I'm going to use through this course are the Nonlinear Control book by Hassan Khalil. Hassan Khalil is a professor at Michigan State University. And the second book is Adaptive Control by Carl Astrom and Björn Wittenmark, and both of them are professors at Lund Institute of Technology in Sweden. Actually, I will be following them very closely. However, for more information, we can refer to the book Nonlinear Systems, again by Hassan Khalil, and the book entitled Applied Nonlinear Control by Slotin and Lee. Slotin and Lee are professors at the MIT, and by the way, Slotin has a series of lectures on YouTube for a course taught at the MIT entitled Nonlinear Control. So I encourage you to look for these lectures and watch them. Some of the material that I'm going to present are taken from these videos as well. Now let us see the difference between linear and nonlinear systems. If we assume a linear system, G of S, so this is linear, and we assume that at the input there are two signals added together, which are R1 and R2, 2, and they are both acting on the system, and the result of the system is y. Now if we take each input separately and apply it to the same system, so take R1 and apply it to G, you get say Y1, and take R2, apply it to G, we get Y2. If we find that the summation of Y1 and Y2, which is the output obtained by each input separately, is equal to the total output that would be obtained if we apply both inputs to the system, we say that this system is additive. Now, if we apply again an input R to a linear system and we get an output Y, if we multiply the input by some constant, so A here is a constant, and apply the resulting input to the system, and we get the same output obtained before but multiplied by the constant A, we call that system homogeneous. Now if a system satisfies both the property of being additive and homogeneous, we say that the superposition principle is fulfilled and the system is linear. So if I say a system is linear, it means directly that the superposition property is fulfilled. So a linear system obeys the principle of superposition. This is the definition of a linear system. If the system does not obey the superposition principle, then we call that system nonlinear. So nonlinearity is reflected directly by the fact that the system doesn't follow the superposition. Now let us see an example to illustrate this. Very simple example. If we assume that dy by dt is equal to an input u, that means that our system is just an integrator. This is u and this would be y. So let us see if the system is additive or not. We assume that if u equals u1, then we get dy1 by dt equals u1. So y1 here would be the integration of u1. If u is equal to u2, then the output would be y2 according to the system equation. Now if we add u1 to u2, then we can write dy by dt equals u1 plus u2. But if we use the above equations here, say equation 1 and equation 2, and add them together, we get d by dt equals y1 plus y2 u1 plus u2. So the input here to the new equation is u1 plus u2, and since the equation has a unique solution, then y must be equal to y1 plus y2, and that proves that the system is additive, because when we applied u1 alone we get y1 alone, u2 we get y2, and if we apply the sum of u1 and u2, and u2, we get the sum of y1 and y2. So this is the additive property. Now if we take u equals a times u1, where a is a constant, then we can write a, I'm going to multiply the first equation here both sides by a, I get a times d by dt y1 equals a times u1, which can be written as d by dt a y1 equals a u1, and again the input, which is u1 scaled by a constant a, would result the same output y1 scaled by the same constant a. So I conclude that the system is homogeneous, and consequently I conclude that the superposition is satisfied, and consequently I conclude that the system is linear. Now let us see a nonlinear system. So another example. If I take y equals x squared, where x is the input and y is the output, so if I apply x1 to the system, I get y1 equals x1 squared t. If I apply x2 as an input, I get y2 equals x2 squared t. If I apply the sum x1 plus x2, I get y3 equals x1 plus x2 whole squared. And it is obvious that x1 plus x2 all squared is not equal to y1 plus y2, which is x1 squared plus x2 squared. So we conclude here that y1 plus y2 is not equal to y3, and consequently the system is nonlinear. So this is just a simple example to illustrate what we mean by linear and nonlinear systems. A natural question to ask now is why we should study nonlinear systems. Actually, there are two main reasons for that. The first one is that most practical systems are nonlinear systems, and we can see that in different examples. Like for example, if I consider here, say, a tank with a valve, and suppose that we have some input rate of flow, I will call it Qi, and output rate of flow Q node. We know that we can control the level of the liquid inside the tank by controlling the opening of the valve. So here we will notice two things. The first is that you cannot close the valve more than 0%, and you cannot open it more than 100%. So here you have what's called saturation limits. It's between 0 and 100%. Furthermore, actually the valve resistance to the flow of the fluid through it will depend in a nonlinear fashion on the height of the fluid inside the tank. So here nonlinearity appears in this physical system in a natural way. Another example that we could consider here, if we take a simple mechanical system which consists of a spring, say with some spring force Fs, and connected to a mass, small m, that has friction with the floor surface with force F, say subscript F, and we assume that there is some force, external force applied to the system, I call it F, and suppose that we measure the displacement of that mass, I'm going the displacement, say y. So by using Newton's law, second law, we can actually write the dynamical equation of the system as m y double dot equals to the sum of forces applied to this mass, and in this case we will have the external force F trying in the direction of y, and we'll have the spring and the friction forces opposing that force. So we'll have here Fs minus friction. Now, as we know, there are different types of friction forces that we could encounter. So for example, we could have, if this is the velocity and this is the force due to friction, so it could, for example, behave like this, and that's what is called column friction. Could have another kind of friction, and this could be column plus viscous friction, and this is normally represented like this. So again, the horizontal axis would be the velocity, and the friction force would be in the vertical axis, and in that case it would be something like this. So this is column plus viscous friction. So the point here is that many elements in nature are actually non-linear, and in some cases linearization does not give us a clear picture about the performance of the system, as we are going to see. So this is the first reason why we consider nonlinear system. Another important reason is that some of the phenomena that we see in nonlinear systems actually do not exist or appear in the linearized version of these systems, and I will consider some of these phenomena here as an example. So for example, there is what's called the finite escape time, and by that we mean that a system response will go to infinity in finite time. This is a phenomena that doesn't appear actually in linear system. In linear system, even if the system is unstable, we know that the response would go to infinity as t approaches infinity. However, let us consider this example. Suppose that we have x dot equals minus x squared with the initial condition x of 0 equals minus 1. Now, if we consider this differential equation, we can actually find the solution x of t. I can write dx by divided by x squared equals minus dt, and if I integrate both sides of the equation, I can find an expression for x of t taking into account the initial condition, and that would give me 1 over t minus 1. Now the important point here is that as t goes to 1, which is a finite time, we will notice that x of t will go to infinity. So in finite time, the output of the system reaches infinity. This is a phenomenon, as I said, that never appears in linear systems. So this is one of the phenomena. Another phenomena that actually appear in nonlinear systems is that it could have multiple isolated equilibrium bonds. And let me take a very simple example. If I assume a pendulum moving around a pivot, this is the rod and this is the mass of the pendulum. So we know that there are two positions where the pendulum can stand still. one of them would be vertically up. So this is the space. So this is the one equilibrium point, and the other one, of course, if we take it vertically down. So if we put the pendulum stand still in the vertical up position or the vertical down position, and we don't apply any disturbance to this pendulum, it will remain there forever, and we call that equilibrium point. So we have here two possible equilibrium points for this system, which is a nonlinear system. However, if we consider linear systems, as I said, the equation x dot equals ax. If I assume that a is non-singular, then we will have just one equilibrium point at the origin. If a is singular, actually there will be a continuum of equilibrium points, a series of equilibrium points, but they are on the same line. They are not isolated from each other. So this is the distinct feature of nonlinear systems that we are going to talk about in detail later on. Another phenomenon which is unique to nonlinear systems is what's called the limit cycles. We know that in linear systems, if we have the eigenvalues of the system or the poles of the systems on the imaginary axis, then the output of the system will exhibit sustained oscillation. However, that oscillation will be, the amplitude of the oscillation will be dependent on the initial conditions of the system. In some cases, we need to have devices that obtain oscillatory response, and that should be independent of the initial conditions, and should be also reliable. Because in case actually of linear systems, any small perturbation to the system will shift the eigenvalues from the j omega axis, and we lose the oscillatory output. So this phenomena can be obtained reliably in nonlinear systems, and it's called limit cycles. So a limit cycle is an oscillatory behavior that appears at the output of the system, and it has a fixed frequency, and it is independent of the initial conditions. We'll talk about it through our coming lectures. Another phenomena which could appear in nonlinear systems is what's called the subharmonic and harmonic oscillations. In linear systems, we know that if we apply a sinusoidal input to the system, and if the system is stable, then the output will have a sinusoidal nature with the same frequency as the input, but with different amplitude and phase shift. The phenomenon that could appear in a nonlinear system is that we could have, for a sinusoidal input, we could have an output that has frequencies not multiples of the input, but subharmonics of the input, and this is again a unique feature of nonlinear systems. Lastly, there is a phenomenon which is called the chaos of the nonlinear systems, and this is actually a random behavior of the system. Although the system is deterministic, the response of the system would behave in a very random way. So that's what I meant by the fact that the nonlinear system could exhibit some phenomena that we don't see in linear systems, and we would like to study that, of course. In our course here, we will talk about the limit cycles briefly. We will talk about the equilibrium points and their stability in detail, and we will see how to design systems to stabilize the operating point. Now we'll move to talk about adaptive controllers. So first, let's say what is an adaptive controller. Actually, an adaptive controller is a fixed structure controller. However, the parameters of the controllers are adjustable. So here it contains adjustable parameters, and of course there should be some mechanism in order to adjust these parameters, and the parameters of course will be adjusted based on the changing conditions that the control system may face. And adaptive controllers are suggested to deal with the uncertainties that could exist in a given system, and as I mentioned before, these uncertainties could be classified as parametric uncertainties, like for example a motor that we don't know its friction coefficient for sure, or the inductance or the inertia or whatever, we don't know the parameters for sure. Or another case where we use a simplified model, so we ignore some of the dynamics, so we call that the unstructured uncertainties, because of some of the dynamics are not shown in the models that we are using for design. So in these cases, adaptive control could be beneficial and used. Now, of course, we have to ask also why we use adaptive control. And there are some cases where adaptive control actually is superior to the common linear controllers. Like for example, if I assume that I have a very simple system, x dot equals ax plus u, where the parameter a is unknown. Now if I use a simple feedback controller minus kx, where k is a constant, then we can write the closed loop equation to be x dot equals a minus kx. This is a scalar system, so in order for the system to be stable, we require the factor a minus k to be negative. However, if we assume that a is unknown, as I assumed here, then I cannot really choose k to guarantee stability of the system in all cases. Of course, the condition for stability is that k should be greater than the magnitude of a. So if a is unknown, then I can't really choose a proper case that would ensure stability for all possible cases. The adaptive controller that would stabilize this system irrespective of the value of the unknown constant a would be given by the relations u again equals minus kx. However, the value of k is calculated from the differential equation k dot equals x squared. First of all, notice that this is a nonlinear controller. Second, of course, we have not derived this relation k dot equals x squared. We will see that when we talk about adaptive control later on. But the point is that this formulation would guarantee the stability of the system irrespective of the value of a. So in this case, the adaptive controller is superior to the linear controller. Another example that illustrates the benefits of adaptive control is a case when we have disturbance. So if we have again a scalar system, x dot equals ax plus u, and I'm going to add here a term that represents disturbance. In order to compensate for the effect of the disturbance, we could choose the control signal to be minus kx minus an estimated value for the disturbance. If we do that, we can actually guarantee that we can eliminate the effect of disturbance on the control system. So these are two cases that illustrate that it is beneficial in some application that we use adaptive control. Finally, let me give a brief introduction to model reference adaptive control. Assume that we have the normal control loop. This is a plant, and this is the controller. With negative feedback. This is the reference, and this is the output. So assume I'd like to have the relation between the reference and the output to behave like some reference model. So this is a reference model. So I like the relation between the reference model and the output of the reference model to be similar to the relation between the reference and the actual output of the system. So what we do is that we devise some mechanism. We call it adjustment mechanism. We take as measurements the output of the process, the control signal, and the output of the reference model, and the adjustment mechanism would be designed some way so that it would adjust the controller parameters so that the closed loop system would behave in a similar fashion like the reference model. So this actually concludes my introductory lecture on this course, and we'll continue in coming lectures.